let me start by briefly reminding what we considered last lecture, the first one. So first we defined the notion of homotopy between functions, continuous functions between two topological spaces. So there is a notion of sort of an equivalence relation, which we denoted by the symbol, and so which relies explicitly on the existence of continuous mapping from x times interval to y, so that at 0 restricted to 0 it gives f, and restricted to 1 gives f prime. And we also studied a notion of homotopy equivalence between two topological spaces, which by definition was the existence of pair of maps from x to y and from y to x. So the compositions in different ways is homotopic to either identity on x or identity on y. And we also showed the various properties. So this is indeed equivalence relation. And if you have homeomorphic spaces, then they're necessarily homotopic equivalent. Then there was homotopy. We defined the notion of paths, and there was a homotopy between paths. So the path was a single path with a function, a continuous map from interval to topological space x. So one can take prism f and f prime, and say they're homotopic as a path. So one can, if one wants, one to explicitly say this is a path homotopy. If there exists a homotopy in the sense that there exists, so f is itself, the function f is called homotopy. It's a function from square to x, which one can depict, schematically depict as follows. So this is f, and here it restricts to path f, and here it's restricted to path f prime. And the condition that both, so for, so this is the direction of homotopy, and this is the direction of where we parameterize our paths. The condition that, here everything is mapped to a fixed point x0, and here everything is mapped to a fixed point x1. So one can visualize this. The image of the square as follows. It's a path f and path f prime. This is fixed point, start point x0 and x. And so we proved a bunch of properties about these things. And we, so at the end, okay, let me, are there any questions about the previous lecture? So we stopped at the following proposition. Proposition star, because I will need to refer to it later on. So there was a bunch of points So here we can see that everything are paths in some topological space X. So first there was a property is path F is homotopic to F prime, then the inverse path is homotopic. The inverses of those paths are homotopic to each other. Then point B is that if F S is homotopic to F prime, path G is homotopic to G prime, then the composition of paths, which we defined in the previous lecture, is homotopic to F prime composition of F prime and G prime. So this was not a composition of functions. This is one can say concatenation paths. And there was a property that we can kind of serve as one can say associativity of the composition of paths, which we can write explicitly as follows. So we define the composition of the binary operation, but it has this property, nice property. And then finally, we want to show that composition of paths with its inverse path is homotopic to, let me denote it by, so if I consider paths F starts at F0 and X1, so it's homotopic to a constant path staying at 0. So this is a function from 0 to 1, which everything is mapped to just constant. So, well, again, let me write it like this. That's the path to X, so that for any t is okay. So let me. So the proof is in many cases the proof is very simple. Let me just do it in a very brief fashion. So first, so suppose we have. Let's start first with the first in a bit detail. So suppose we have some homotopy which realizes this, and so we can take, of course, so we want to find F bar homotopy F bar, so that this realizes homotopy in F bar and F prime bar. So of course, if this was, one can take F bar of S and T to be F of 1 minus S and T. So if I use kind of this diagram to show that so my F here was by this F, so F prime is F bar. Can be depicted like this, and just inverse the direction of paths. Is this clear? So the second part is that the composition of paths is expected. The homotopy expects composition of paths. We can so explicitly realize the homotopy, let's say H between compositions as follows. So we have, suppose we have some homotopy between G and G prime, and then homotopy between F and F prime. So here we can decompose them. And so we want to do, so this was, suppose big F is homotopy between F and prime, and big G is homotopy between G and G prime. What we essentially do, we rescale these two squares in one direction, and we combine them together.
Do you want to make it different structure?
Just change F to make capital and G capital in the diagram.
Oh, thanks.
Last week you defined the composition of F. It is the F first and G.
Yeah, it's the other way around. First F and then G.
Oh, really?
F1 is 0 defined.
Yeah, I think in the, when we
I think
were
it's probably better like to define this. Well, let me define this as. Sorry. Well, I want to say that this is a function of S. So this is a function from 0 to 1, which sends S to this. So I think everyone says, yeah.
So it's not as well, because if S is 1, you have like
Yeah, let me define like this. So it's kind of in this way. Sorry about previous time, but in this way, it's kind of more similar to the composition functions. But I mean, it's not really. So you see, so in this definition, what we do, we just kind of rescale these functions and combine them together. So here, we just do the same thing for homotopy, so we rescale them. I mean, in one direction, we rescale the squares, which functions from squares, which are always homotopy in one direction. So C. So this is probably maybe the most non-trivial thing. So we want to show this. So let's see. So in the big, so let's first see what we have here. So here we can restart. So when we compose H with something, we start with H and we put something here. And then we compose here G with F, right? Again by scaling them both by half and combining them together. So this is 1/2, 1/4, and this is 1/4 of integral. And we want to make it homotopy to this, to realize homotopy to the following thing. HG. Right, this is 1/2, this is 1/4, and this is 1/4. So again, this can be realized by just doing rescaling, which depends on my homotopy parameter T. This is parameter S, which parameterizes the path. So in the picture, it's pretty clear, but of course, if you want to write an explicit function, this maybe it could be ugly, but please let me. Suppose this is a homotopy K, so this is a function from square to my topology X. So if I'm not mistaken, didn't have my mistake. Should be explicitly written as follows. this is a scaling which so at each point of t, I kind of define here just the same h functions, h, g, and f. So they are appropriately argument s is appropriately rescaled and shifted. So the final statement is that f in f bar is homotopic to a constant path starting staying at x0. So let me to realize this homotopy, let's say again h. So let me start with kind of a trivial homotopy. So homotopy from f to f inverse to the same thing. So it's just a constant, just a function which is constant along the vertical direction. And then let me modify it as follows. Let me say that here I will replace it by a constant function. So this is indeed compatible because the value of path, the value of path at this point is the same as the value of the inverse part at this point, right? So this is so this way I get a continuous function from square to x, and so at the end, so when t equals 1 here, at the end I will just get a constant function which stays at x because all this side maps to x, and so this was the middle here. It mapped to x1 and the end point. So you can visualize this as follows. So you have path f, you have path f inverse. So f started at x0 and ended at f1. So what you do, you just gradually erase here, right? And you end up. Okay, now finally everything is prepared to define fundamental group. Fundamental group, which will be denoted by 1 x0 of the topological space x and what is called the base point, which is a choice of point x. Homotopy classes of paths starting and ending at x0. So in this case, so if path starts and ends at the same point, then we can call, of course, it's natural to call it loop. So this is the definition. So okay, this when you think the homotopy classes, this defines as a set. So this is actually not the whole definition. We have to say what is it, since we want to say, want it to be group, we want to define a group structure. So this group structure so by F I denote a homotopy class. So this is a homotopy class of F. I want to define group multiplication, so if I take another element of the set, the multiplication should be a homotopy class of the composition of two paths. So again, of course, if so first of all, it's so let me argue that this is a well defined. This is a definition, but we have to.
But we have already got this from part E of the proposition.
Yes, exactly. We just want to refer to the letters. That's why we need this proposition. So first of all, if we have a path starting and ending like 0, another path starting and ending at the same point, so the result of the composition will also have the same start and end point. So it's all with this loop with the same base point. And so let me put the following remark. So the composition F and G as a map is well defined. Due to proposition star part, well, let me say star part, right? Because if you take another representative, which would be a homotopy equivalent to F, if you take F prime and FG prime, which are, the same, are different loops, but belong to the same homotopy class, the result of the composition will also have the same homotopy class as F and G. Okay, now, so this gives a well-defined map from well-defined map from part x x0 times itself to itself. But not every, of course, not every map like this can be is a group multiplication. We have to check group axioms, right? Group axioms are satisfied. So how do we see this? So first is existence, first group axiom existence of identity. And so this is indeed true because identity can be realized as a homotopy class of a constant map staying at x0, right? So if we add, if you combine, if you combine the map with some constant map, it will be the same of the same homotopy class. So for any the other condition is existence of inverse. For any f, they exist inverse. And this can be realized as f bar. So we need the exist inverse such that the product of f is f inverse, or the other way around, is the same as identity. And this is indeed was proved by proposition star part D, right? So we showed that. So first of all, we use the definition of multiplication. So this says that the result of the multiplication will be homotopy class of composition of f with f bar, and in the proposition part D, we showed that there is a homotopy equivalent to constant path, which is identity in our group of homotopy paths. And so the last property is what we want to show is that associativity is that so we can take multiplication in this way, in this order, or in this order of 3 guys, and this should be the same. And this indeed follows directly from proposition star part C. So this concludes the proof that this is indeed defines group structure. This map is well defined, and indeed satisfied. Questions?
Why P1? Why this? What does it mean? This subindex 1 in the group, in the fundamental group?
Oh, because this is a kind of one-dimensional. It's a homotopy. Well, the analogs of high homotopy groups, which have this other index, other natural number index. Well, not just, I mean, any integer actually. I mean, this one means that we consider kind of maps from S1 to X, which is groups. But for higher pi n, let me not go into details. You can see maps of Sn to X up to homotopy. So as I mentioned in the very beginning, so this is one of the examples of these maps which connects kind of from topology to algebra. So given a topological space, this produces some object in algebra, some group. And more with this kind of map between topological spaces to groups. There's some very nice properties. First important property is that for a path connected space, X, so if I take fundamental group with base point x0, it will be isomorphic to the metal group with base point in x1 for any x0, x1, any 2 points in x. So that is a proof. So x is path connected. Then by definition, there exist paths H from 0 to 1 to X such that H0 is X0 and H1 is X1. And we want to use this path to explicitly construct isomorphism between these two groups.
You conjugate by?
Well, more or less. So let me construct following map from pi1 x0 to pi1 x1, such that if I take a homotopy class of a path f here, it's mapped to the following loop. So how can I visualize this? If I have some loop f, some loop f, and which so it was with base point x0, and so here, suppose here I had x1. So what I want to do is I want to h, so let me see, h goes from x0, this is h and this is h bar, kind of repeats, so repeats the part. This is h and this is h bar. So they have the same trajectory, but they go into different directions. And so for this combination, so I go h bar, I start at x1, I go along h bar, I go along f, and then I return using path h. So this gives me some loop. Starting, so I was doing a loop starting length in x0, and I ended up with a loop starting length at x1. Okay, and of course, due to all these propositions, this is well defined. So it doesn't depend, because it doesn't depend on the homotopy, on the choice of the representative f. But what we want to show is that it's not just a map, it's we want to show that the H is a homomorphism. First. Before showing that this is isomorphism, we want to show that this is homomorphism. Homomorphism. It's a homomorphism so that it respects group multiplication. And this can be explicitly shown as follows. So suppose I take a product and I want to use map BH, act by BH on it. So it will go to, so this is the same as a composition of F and G, as we showed before. And so then I use the definition of my map. Using this representation, I use the definition of map PH. Then, of course, as we showed, we can kind of forget about brackets when we consider paths up to homotopy, and then so we can recombine brackets. Follows. And since this is a homotopic to constant path at x0, we can replace it by our trivial paths. So this is the same as I continue with this chain of qualities, we end up with this. Which is, sorry, did I
Jesus.
My logic was a bit flawed. So let me, I'm sorry, let me repeat it again. Well, all equalities were correct, but so okay, I start with this, so I have to by map BH. Right? So this is a definition. And then I do this kind of, I want to go in a different direction. Then I first recombine and brackets and I replace, insert identity here. And because this is a homotopy to a constant one. And then I use the definition of multiplication in this group. So I can combine, take brackets like this and this. So I end up having the multiplication of homotopy classes represented by those two guys, and then this is by definition the product of image of F under BH and image of G. And this was, we proved that so BH of F so it proves the following. So BH of a product of two elements of the group is the same as product of so then indeed we show that BH, so by definition BH is homo.
The space is not bus connected. Can we know the fundamental group of the whole of the space from the maximal components?
Well, we know it's essentially so. If 2 points can be connected, bus connected, then the fundamental groups associated to those points are again isomorphic. Because the only thing we use here is that the 2 points can be bus connected.
Yes, but if the space is not bus connected, then we have the maximal bus connected components, right?
Well, there are a few path-connected components, right? And there essentially will be some group associated to this component, some fundamental group. After isomorphism, there will be unique group associated to each path component.
My question is, the space as a whole, as a fundamental group of it, can we relate it to this group? Direct sum or product? Or?
No, what do you mean the fundamental group of the fundamental group of the space itself without a fixed main point is only defined in the when it's paths connected.
Okay.
So this is what I actually want to remark on. So if X is path connected, then one can talk about phi 1 effects. Since if you're considering groups up to isomorphism, sorry, okay, before, actually I didn't quite finish my point. So I showed that this is a homomorphism, but I want to show that there is inverse. There is inverse, there exists inverse homomorphism, which is can be it's obvious that it's can be realized by P is taking H to be replacing H by its inverse, right? And so then by definition BH is Heisenberg. Okay, so this concludes the proof of the proposition that so after isomorphism, So then we show in particular the corollary that is, so if X is path connected, then one can talk about, if you consider fundamental groups up to isomorphism, then we can just talk about fundamental group of the space.
It should be part of definition of fundamental group.
Hmm?
It shouldn't be part of definition of fundamental group.
Well, so yeah, I mean, if you want to define this kind of thing, which only depends on X, but doesn't depend on the choice of point, then it's you can define it as isomorphism class of all previously of fundamental groups with fixed base point. But let me, I mean, it's important to know that, so there was isomorphism. So let me, I mean, this is a bit subtle point, but it's might be important. So there is, we showed that there is isomorphism, but what it's called is it's not canonical. People might say it's not canonical. Not canonically isomorphic. So if you chose a different path H, in general, it might happen that the isomorphism is a different isomorphism. And this is a kind of so some of the exercises are actually about this phenomenon. So I mean, whenever so we should it's like when you want to define a group structure, you have seen that it's important to choose a class. So even people, I mean, when people write like this, they still have in mind some fixed base point, just the statement that we can move this base point. We can change this point after isomorphism this group. Because I mean so this kind of this pi1 is indeed can be understood as the following map. It's topological spaces up to homeomorphism. Well, we didn't show yet the invariance under homeomorphism to groups. So let me say path connected groups. So again, the classification, the problem of classification of topological spaces, it's often considered up to, we want to classify space up to homomorphism, but the groups is also, classification of groups is also usually considered up to isomorphism. Because otherwise, for each isomorphism class, there will be one groups. Okay. So then, okay, let me mention the following definition. So X is path connected. Then, path connected. X is simply connected. Isomorphic to trivial. This is the definition of X being simply connected. So why this is kind of natural words, natural phrase, simply connected, is because of this.
Every class can be deformed to a point.
Yeah, so all, so this, okay, it's, so it's kind of, so part of the phrase is that it's connected, right? So all, what does it mean simply connected? So what it means connected, that all points can be connected. But as far as the simply connected, is all paths F 0, 1 to X for any fixed X0, x1 in x, so that those are start and end points are homotopic. So if you fix, this means if you fix to start and end point of any path f, and take any other path of prime, it can be deformed. They can be deformed in each other. So how can one show it? So suppose we take two paths f, right? Any two paths. This. So let me pick up any fixed start and end points. So let me then consider the following the composition of f prime bar. Okay, so let me. I mean, it doesn't really matter. So this is defined. So if I inverse, I consider f prime bar. This inverses mediation. So this gives me some loop in this base point x0. So it defines its homotopy class, gives me some element of this fundamental group, which we know that it's isomorphic to 0. So it should be just identity element. I mean, 0 means trivial, it's just identity. But from other point, from this it follows that one can. So it follows. So identity can also be represented by constant paths. And so it follows that f prime bar composition with f is homotopic to constant paths. So let me multiply. So this kind of equality up to homotopy, I can multiply it on the left by f prime. So we showed that the kind of if you consider paths up to homotopy, we don't care about the ordered brackets. Then we can put brackets here, and then this is homotopic to a constant path at yeah, x1, and from this it follows. Basically, if there is no, if this is like any loop is contractible, this means that this path, it follows that this path can be deformed to this. Okay, let me, so now we want to show our first theorem, which, I mean, intuitively it might sound obvious, but to prove it rigorously, it's actually a bit non-trivial, and we will have to spend some time to actually show it. So the fundamental group of a circle, which is, because circle is path connected, so it doesn't care about choice of base point, is isomorphic to infinite cyclic group. This is a group of integers with respect to addition. And so let me make the following remark. So what is S? S1 I want to represent as the quotient of real line divided by action of group Z, which is more, explicitly can be written as follows. So real line is a set of real numbers And so this quotient means that we quotient of this following equivalence relation. So the t is declared to be equivalent to t plus n for any integer. For any integer. But of course, this is the same, it's more explicitly can be realized as a quotient of interval by, and it's fine 0 and 1. Then, so if you choose this explicit realization of S1, then the statement is that y1 of S1 with base point 0 using this realization. So the class of 0 in this quotient is generated by the following loop. I want to study map, consider map of interval to S1, so that S is mapped to essentially. Well, let me, to be more precise, let me class of S. With respect to this equivalence relation. So of course this is a closed loop because 0 maps to 0 and 1 is also is in the same equivalence class as 0. So this statement is a part of, can be considered as a part of the theorem. So we need only one generator because integer numbers, they are generated just by 1 with respect to addition. So proof will be later. Before making a proof, we need to make some preparation. Again, so let me just briefly make a motivation. So the n. So what is this kind of? So morally speaking, kind of intuitively, we consider the phi 1 is so we consider kind of loops up to term deformation, right? And so this n kind of the loop. We can consider the loop which winds n times. So this maps to an integer n. So this is more of this isomorphism. But so we actually, I mean, it's, the fact is obvious, and that means it's easier to prove. It should be easy to prove it. But it's not, it's not so easy actually. Well, it will be easy after we do some preparation works, a bit of preparation. Which there will be some intermediate results which should be useful for some other things. First thing we want to do is to introduce the following definition. Covering space x tilde of topological space X topological space, which denoted by X tilde, and the map together. So we want to keep additional information together with the map. Of course, continuous, as always, in this course, such that for any point x in big X, there exists an open neighborhood of x0 such that the inverse image of U under map P is a union union of open sets shared node by U tilde with index alpha, where alpha runs on the certain set, so that each pair of different of different guys here is so it's a disjoint. I can say this is a disjoint. I don't know if you're familiar with this notation. I can equivalently write it like this. Disjoint. So what end? So this is not everything, not the end of the definition. So there exists an open neighborhood such that the inverse is a disjoint union of open sets, which doesn't say much, but we also want the following condition. If P is restricted to one of the guys in here, so each guy, of course, is a subset, some open subset of X tilde. So this defines, if I restrict on U tilde alpha, it's giving this map. And I want it to be easy. Homomorphism. So this is a bit abstract, but okay, well, how does this morally look like? So if you have some sort of X and X tilde, some covering, so if we take some, so the statement that there exists for any X tilde point X, we can choose some neighborhood. Open neighborhood U, so that the preimage is a bunch of disjoint neighborhoods like tilde alpha, so that each of these, if I restrict P to any of them, this will be isomorphism. Sorry, homomorphism. Essentially, each neighborhood just leads to a bunch of its copies.
Does it mean that locally it is like a product of the spaces, of the space with itself? Locally.
Well, locally it's a product of original guy and this index, essentially this set I or which.
So it's just a product, but at every point the number of the copies can differ from another point.
No, actually, it's not possible.
How? But here, like we have some number of copies of the same neighborhood U because.
Well, okay, if it's connected, okay, well, if it's paths connected, then it can be.
Okay.
Yeah.
Is this definition of coding space similar to, or maybe related with the Gaussian maps somehow?
Yes, you can. So some of the covering this map. So there is some statement that yes, the covering map can actually be always realized as a quotient. So there is some sort of what is. I mean, if you have time later, we can see this. So there is some sort of what is called deck action on this map, and which defines some equivalence relation, and then this map can be realized as a quotient with respect to this equivalent relation of this action of the what is called deck transformation. But yeah. But for now, we don't need this.
Okay.
But yeah, it's true that this always can be realized as a quotient. But not all quotient maps are covering, but the other way it's true. All coverings can be realized as a quotient maps. So actually, in one of the example of the covering which we will need to use is indeed. So we want this. So example of covering the map from R to S1, and indeed in this case we can say that P is a quotient sorry, I think I want to use variable s here. I mean, it's not important. So I can visualize this as well. So we have S1, and I can represent kind of R as some sort of helix, infinite helix. And so if I take some X, I have some open neighborhood, it's lifted to a bunch of open intervals. I mean, the helix is kind of, you can understand it's kind of considered above S1. Well, the points, so this is a topology, this is a real line, so the points which differ by integer numbers, they mapped, they projected to this symbol. Let me make another remark, is that so U neighborhoods. So open set U in X satisfying object as as a definition of covering is called evenly covered. By property, I mean that it's a preimage with respect to covering map is a disjoint union of open sets, such that if restricted, if covering map P is restricted to any of them, it provides me with homomorphism to. Questions? So let me, the definition of f, let me say f tilde is the map from x, from y to x is a lift. So the definition is a lift of map here x tilde is a lift of map y to x such that as a following diagram is commutative. You're familiar with the notion of commutative data. I mean, this is just statement that I can, like this map, I can go in any direction. So the composition of this map is the same as the composition of this map. So the lift is often denoted by dashed line. So because it's so given f and p, there might be a question: does it exist or not? That's why it's often denoted. Like if there's a question of existence, it's often denoted by this dashed line.
So could you please repeat the definition about heavily covered?
Yes.
I missed the definition.
Okay. The definition. So it was just a repetition of what was the property which was spelled out in the definition of covering. So let me repeat it. U is x is evenly covered. I mean, we mean evenly covered with respect to a certain covering. If so this is a disjoint union of a bunch of open sets in X tilde, which means they're pyrrhoids. The different guys here are pyrrhoids, have pyrrhoid zero intersection. If and p restricted to any, for any alpha, p restricted to u tilde to one of these guys, which can be onto the map from it to u, because this guy is an image of u, is a homomorphism. Like in this example of a real line covering S1, evenly, you let me, so this is open. So for example of evenly covered guys are open, like open arcs in S1, so they lead to the joint union of open intervals in R.
So we don't see the infinite helix as the covering, but just the real line. That's what the example is.
Well, the helix the infinite helix is a real line. And this is so if I realize that kind of helix embedded into R3 is three-dimensional space, this is covering and this is the projection of the plane where S1 lies in this three-dimensional picture. So this is a covering, and an example, I can take any arc, kind of not closed arc here, and it will be evenly covered by these kind of intervals. I mean, like one can write explicitly, like if AB is, I can realize some sort of S1. Well, I mean, it's clear geometry. And what the more here more specific is the lift. I mean, of course, we are talking with respect to P. So in principle, the lift can be considered with respect to not just current mark, but any mark. But for us, we assume here this is the current. Now I want to prove the following proposition is for lifting criterion for certain cases, for certain case of y, this lifting criterion when this lift exists. And kind of once we prove this proposition, it will the theorem about fundamental force 1 will more or less immediately follow from it. But this proposition is very useful in general when studying coverings and asking questions about existence of lifts. So let me fix f of y times interval.
Sorry, but are covering spaces of some space isomorphic, or can a space have non-isomorphic covering space? If I have
well, well, you can cover S1 with. Let's see. Well,
because
no, for S1, I think the only thing you can have is R.
Because it seems like a universal property of X, of the covering space.
Well, I mean, in certain cases you can have unique covering, but in more complicated cases there might be not a unique covering. I mean, up to common. And so there is actually a question, I mean, an important question, so given X, can we classify coverings? And if you have time in the course, actually, I mean, the fundamental group is very important for answering this type of question. What is the kind of homomorphism class of coverings or fixed? But in this case, it's all coverings in the region are. So, okay, where we were. Okay, so we fix this map from y. So we consider actually, the map from y times interval to x, and fix another map f0, which will be f tilde 0, which will be mapped from y to x, which is the lift of f, the regional guy f, restricted to y times 0. Okay, yeah. So this is if I restrict, this gives me more. Oh, sorry, what am I? There is x tilde. So so I fix, so I fix this guy. I fix also covering. The map from y to x, and the map from y to a cover space, x tilde, which is the lift of this map from y to the x itself. Such that, okay, so I do this, then there exists a unique f tilde, which is a map from y times interval to x tilde, which is the lift of f. Okay, let me draw a diagram. So we have x, sorry, so we have x covering of x by x tilde, is a map P. So we have a map from y times interval to x. This was f. And we also can consider a subspace here, which is just y times the beginning of the interval. So it's just canonically embedded. And so this map can be understood as a restriction of f and the subspace, the composition of inclusion and f itself. And then, so what I'm given, what I'm given is I was given existence of the lift of this guy, of this map. And the statement is about existence. So once given all those guys on dashed line, not non-dashed maps, so everything is commutes. The statement there exists a unique lift like this. So yeah, so here's the additional condition of the lift is that, of course, if I restrict the lift on the zero here, it should coincide with this fixed lift. So to summarize, if you have a map, so we only consider study lifts, not just like of some maps from y times interval to x with respect to some covering. It's enough to just give if once we're given a lift of restriction of this map at the beginning of the interval, this should completely determine the lift of the map itself. Is the statement of the theorem clear? So the proof will require a bit of kind of analysis, which a bit technical and not very exciting, but you have to bear with this. This proposition. Okay, so let me start with this one. So take any point y0 and y, and so let me take this part 1. Take any y0 inside y and show that I want to show that there exists neighborhood n of this point such that there exists unique, so we want to construct a lift restricted on this neighborhood. So this is what we don't want to construct. In the first part, we don't want to reflect the lift on the whole y, but we want to construct the lift on just on like for any point of y within its neighborhood. We want to construct the lift. Let me try to draw something here to make it more clear. So suppose I have some space y, have some point y0, some neighborhood m, and but then I have actually I have y0 times interval, so the product roughly speaking looks like this, and this is pretty schematic. And it's mapped. So this mapped some space x, and there is some space still here. So f takes the whole product to x. So f is continuous. This means that for any choice of a point in this product, so let me fix some point, also some point in the interval. So this fixes, of course, me a point, of course, in the product. So any point, there exists a neighborhood, which I will know by MT, depending on T, for this part. So this is a neighborhood. Such that this is neighborhood inside.
Why?
Inside y times such that the image of this neighborhood belongs to some neighborhood, open neighborhood of the point. This is open. This is the neighborhood of f of y0 t, which is evenly open, and it's required to be evenly So first of all, okay, so I take some point. So if I take any point here, right? So by the definition of this covering map, there exists an open neighborhood which is evenly covered. So this is the image of y0t. This is u. And then since F is a continuous map, the preimage of this open set should be an open preimage of this open neighborhood should be an open neighborhood containing of this guy. So this is F minus 1 u. But of course, we know that the topology, so here we have a product space, and the topology of the product space is generated by the products of open sets, right? So we can always choose here a product, the neighborhood, which is a product of open neighborhood in the interval times open neighborhood in Y, right? So this is so this is our space MT times MT. So you can always choose this kind of product of open neighborhood inside this. Okay, so this. So we do like this. So we pick up this kind of square, MT, I mean, it's not a square, but product of MT times interval. So now, of course, we want to use a fact that 0, 1 is compact. And we can choose finite color of the guy by I can say subcolor of 0, 1 by unions. Well, of course, if it's at the end of the interval, this can be square. So we choose, I mean, for any t, we chose some sort of interval, but of course we can, the point is that we can choose just some finite number of interval which covers the whole compact.
What about the endpoints? This AT and BT, does they contain also the endpoint 0 and 1?
Yeah, well, if, so if you take for here t was considered an interior point, but of course, I mean, there is some special case when t is endpoint, then of course this would be just, in this case it would be 0, so for the base point it would be 0 here, and we put it. So it's, I guess I have to stop here. So, okay, let me just make, so final, okay, just consider, just finish this thought. And then one can show that there is, from this, I mean, it's not at the end of the theorem, but there exists a partition bunch of points, the finite number of such that for any I, f times any closed interval between a pair of neighborhood points, Ti, belongs to some UI, which is even covered. Okay, we'll have to continue next. Any questions?
We haven't finished.
Yeah, we have.